Okay, this video is for calculus, the unit with parametric equations, polar and vector. This one is a follow-on to the polar definitions that we talked about. Now we're going to talk about doing calculus with polar. Specifically, this application will focus on derivatives using polar and tangent lines, and then arc length, and we'll save another video to talk about area and polar. This one only has 3 examples, but they're pretty long, especially the first one. But I'm choosing these examples because they are really thorough and they illustrate certain things. So bear with me, and remember you can pause the video if you need to review things. You can always try these problems with me. All right, so first, we know that the equations to convert from polar to rectangular are x is r cosine theta, y is r sine theta. They're almost like parametric equations because they express x and y in terms of other variables. But since we usually write r as a function of theta, then that means x and y end up being a function of theta. So this is all real abstract, but let me give an example. Let's say that r is 4 cosine theta, right? And that means if x is r cosine theta, and this r can be replaced with 4 cosine theta, then that means that the x is 4 times cosine theta, which means x is a function of theta. And then y is also that same r of 4 cosine theta, but times sine theta. And that means y is also a function of ultimately one variable. So you can think of this as a set of parametric equations where the parameter is the angle theta. Right, so all the things that we can do with parametric equations, we can also do with polar. For example, we can define the slope, dy dx, as dy d theta, the parameter, divided by dx d theta. It's not important to know this specific thing. It's interesting to kind of see that, but I just think of it this way and build it on the fly directly from this. So if I needed to find like the slope of a tangent line to this function curve right here, I could write out the equation for x, write out the equation for y, take the derivative with respect to the parameter for y, and divide that by the derivative of the x with respect to the parameter, and I have an equation for the slope, right? And it's also true that horizontal tangents, they occur for a function curve wherever the slope is 0. So that would be when the numerator of the fraction is 0, which is dy d theta. And vertical tangents will occur when this slope is about to divide by 0 because it's going to an infinite slope, and therefore where the denominator, where dx d theta is 0. Okay, rather than trying to memorize a whole set of things, I just try to picture in your mind what's going on here. This is the key, that the slope can be written by the product or the ratio of these two derivatives, and then just figure out what's going on the fly. Okay, so we're going to use this result to locate angles and points where horizontal or vertical tangents occur. So this is a pretty long example here, but I chose this because it illustrates pretty much everything that can come up. So this says find the points of horizontal and vertical tangency, which I'm interpreting to mean as find the xy coordinates of any points where this curve has a horizontal or a vertical tangent, and then find the equation of the tangent line specifically at theta is pi over 3. Okay, so there's 3 parts to this. There's vertical tangents, horizontal tangents, and the tangent line. Let's start with the vertical tangents. So we'll start with that on this screen. I'll move to another screen for the other ones. Okay, so what about vertical tangents? Well, whatever this curve is, okay, whatever it is, that means that a vertical tangent, right, would be a place where this is undefined, where the slope is undefined. So I know that dy dx, this is the thought process I go through, is dy d parameter, which is theta, divided by dx d theta. And for this to be undefined, that means the slope is going to infinity. It means this is going to 0. So what I'm looking for is the derivative of x with respect to theta, and where are the places where that goes to 0. So I would go through this little thought process whenever I see the phrase vertical tangency or vertical tangent. Okay, so now the goal is to come up with an equation for x. Right, so first of all, x is r cosine theta, but r is 4 sine theta. So that is 4 sine theta times cosine theta, right? And then I need to take this derivative, dx d theta, and figure out where that's 0. So dx d theta, this is going to require product rule, right? So that's going to be first times derivative of the second, which is negative sine, plus the second cosine theta times the derivative of the first, which is 4 times cosine. Right, so let's simplify that a little bit. Make negative 4 sine squared of theta plus 4 cosine squared of theta. I could write it like this. See, that's going to be a 4 times cosine squared of theta minus sine squared of theta. Okay, so now that I have a pretty compact expression for dx d theta, I'm going to force that to be equal to 0 so that my slope is about to divide by 0, so I get an undefined slope. Okay, and therefore vertical tangent. All right, so for this to be true, that means that we're going to have to say either 4 is 0 or this cosine squared of theta is 0. So this cosine squared minus sine squared has to be 0, right? I think what I'm going to do is let's convert this all to either sines or cosines. So we know that cosine squared plus sine squared off on the side equals 1. So that means that the cosine squared could be replaced with 1 minus sine squared. I think that'll help. This we're going to replace with 1 minus sine squared of theta minus another sine squared of theta equals 0. So that means we've got, let's see, 1 minus 2 sine squared of theta equals 0. If I move that to the other side and swap, I've got 2 sine squared of theta equals 1, or sine squared of theta equals 1/2, right? Which means that sine of theta would be plus or minus the square root of 1/2, which is plus or minus the square root of 1 over the square root of 2, which is plus or minus 1 over the square root of 2, which if I take square root of 2 over 2 on top and bottom, is plus or minus the square root of 2 over 2, which is nice because these are places on my unit circle that are one of the 16 special values. So where is that true? Where the sign is plus or minus the square root of 2 over 2? Well, that could be any of the 45-degree lines because it could be positive or negative. So that means it could be, the angle could be pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4. Okay, so there are 4 angles where we could potentially have tangency here. All right, so let's go ahead and analyze that further. We'll take each one in turn. So first, if theta is pi over 4, then that means we should be able to find the corresponding r for that. R is 4 times the sine of that pi over 4. So that would be 4 times sine of pi over 4 is square root of 2 over 2. So that's going to be 2 square root of 2. Okay? And if I want the xy coordinates of that, the x would be r cosine theta. And now that I know the r is 2 square root of 2 times the cosine of pi over 4, that's going to be x is 2 square root of 2 times cosine of pi over 4 is the square root of 2 over 2, right? So that's going to be these two cancel, these two multiply together to just give me a 2, right? And that gives me the x. The y is r sine of theta, which is 2 square root of 2 times sine of pi over 4. And that is y is 2 square root of 2 also times the square root of 2 over 2, which is another 2, which means 2 comma 2 is one point where we have a vertical tangent to this curve. All right. All right, so now I'm going to do that for the other angles as well. So let's do the next one. Theta is 3 pi over 4. So that means r is 4 times the sine. I'm getting this from the equation here. 4 times the sine of 3 pi over 4, which would mean r is 4 times, let's see, sine of that is also square root of 2 over 2, which is 2 square root of 2. And then the corresponding x and y. X is r cosine theta, So that's going to be the r of 2 square root of 2 times the cosine of 3 pi over 4. So that's 2 square root of 2, but the cosine of 3 pi over 4, that's a negative, right? So this is going to be times negative square root of 2 over 2. So that's going to give me negative 2. And then y is r sine theta, or 2 square root of 2 sine of 3 pi over 4. But that is 2 square root of 2. Y is still positive here, so that is going to be positive square root of 2 over 2, which is positive 2. So I have negative 2 comma 2, right? And so there's 2 points of vertical tangency. Okay, let's continue. I'll do the same thing a little bit further down here. So what if we have, I'll do theta over, theta is, see, the next angle is 5 pi over 4. Right, so what would the r be for that? R would be, let's see, 4 times the sine of 5 pi over 4, which is going to be equal to 4 times the sine at 5 pi over 4 is negative. So negative square root of 2 over 2. So this is negative 2 square root of 2. And then if I find the corresponding x and y for that, x is r cosine theta, which would be negative 2 square root of 2 times the cosine of 5 pi over 4. And the cosine of 5 pi over 4 is negative, so that's going to give me x is negative 2 square root of 2 times negative square root of 2 over 2, which gives me positive 2. So this is the point, well, let's do y. Y is r sine theta, which is negative 2 square root of 2 times sine of 5 pi over 4, which would be negative 2 square root of 2 times the sine here is also negative, so negative square root of 2 over 2, which is 2. That gives me the point 2, 2 again, which I already had up here. And actually, if you do the 7 pi over 4, you also get this again. So there are actually 2 points of tangency. The final answer is we have a vertical tangents at the points 2 comma 2 and negative 2 comma 2. Okay, so let's actually graph this function to see if that is in fact correct. So we'll take a calculator, we'll put it into polar mode. It looks like it already is here. Let's clear out what's already there. And this is just one curve, which is 4 sine of the theta. Okay. If I graph it, zoom 6. Okay, it looks to be a circle. Let's zoom in a bit, maybe to negative 5 to 5 or something in x and y. 5 to 5. And we'll zoom, yeah, let's square that up. All right, so here is, now what I'm seeing here is a vertical tangent would occur here. And sure enough, that is at the point 2 comma 2. And a vertical tangent to this curve would occur here, also at negative 2 comma 2. So this is verified by the graph. A lot of work to be able to do that. Okay, that's the vertical tangent. Now, let's do horizontal tangents. Okay, same thing. I would go through the same thought process and say, okay, if I have my curve, whatever, horizontal tangents happen when the slope is 0. And since the slope is dy dx, which is dy d theta over dx d theta, that means that for this to be 0, the top has to be 0. So I need to find out where dy d theta is equal to 0. So the slope is 0 because that gives a horizontal tangent. All right, so we'll start by coming up with an equation for y. Y is r sine theta, but the r is 4 sine theta. So this is 4 sine theta times sine theta, or 4 sine squared theta. And if I need that to be equal to, what, we got to take the derivative first. Let's take the derivative. Dy d theta, let's see, I could do this with extended power rule. So bring this down, that's going to be 8 times sine theta to the first times the derivative of the inside, which is cosine theta. So that's going to be 8 times sine theta times cosine theta. Right, and that is what has to equal 0. Okay, so for that to be true, either this is equal to 0 or that's equal to 0. The 8 cannot be 0. So if sine of theta is equal to 0, that happens here and here at theta is 0. That's a theta. Theta is 0 or theta is pi, right? And the other one is if cosine of theta is 0, which happens here and here when theta is pi over 2 or 3 pi over 2. So I think I've got 4 angles. Probably not all of them are going to produce unique points, but we'll go ahead and start analyzing those. All right, let's take the first angle. Theta is 0. We'll plug that in to this equation to find the r. R is 4 times the sine of 0, which is 0. So the radius is 0. Okay, well, if the radius is 0, then that is just, well, let's continue doing that. Let's go all the way through this point. R of 0 is the origin. Actually, I don't have to figure out the x and y. The only place we have a radius of 0 is the origin, so that means the x and y are automatically 0, 0. So that is a potential point of a horizontal tangency. All right. Next one would be theta is pi. So r would be equal to 4 times the sine of pi. But since sine of pi is also 0, this is also 0. So that gives me 0, 0, which means I don't have to add it on as another. It's still 0, 0, no change. Okay, one of these other angles hopefully will give me something more complicated, or something more, the other point of horizontal tangency. So the r would be 4 times the cosine of pi over 2. Cosine of pi over 2 is 1, so that is 4. So I will have to actually figure out the x and y here. This is r cosine theta. The r is 4. The cosine is pi over 2. And since that is 1, that's going to be a 4. For the x, is that right? Let's just double check here real quick. There's the graph. I think it's the y that should be. Wait, cosine. Sorry, cosine of pi over 2 is 0. Sorry, this is 0. So yeah, this is 0. So this actually would be 0. X is 0. But y is our sine theta. And 4 times sine of pi over 2. Sine of pi over 2 is 1. So that's 4. So 4 comma 0, that would be a point of horizontal tangency. And then the final angle, theta is 3 pi over 2. The corresponding r would be 4 times the cosine using, oh, I see what I did wrong there. You know what? Going a little too fast here. Let me back up. I made a mistake there. All right, let's go back to this again. If theta is pi over 2, r, we have to use this equation for the graph. So that is actually 4 sine of pi over 2, and 4 sine of pi over 2 is 4. So the rest of the computation was right, but that should have been a sine. Let me repeat that again. X is our cosine of theta. So that is 4 times cosine of pi over 2, but cosine of pi over 2 is 0, so that is 0. X is our sine of theta, 4 times sine of pi over 2, but that's 1, so that's 4, so sure enough, this is 4, 0. The problem was I had written sine, cosine there, but it's actually sine. Okay, let's do this now correctly. This is 3 pi over 2 here. The r is 4 times the sine of that angle. And the sine of that angle is negative, right? Sine is -1, so that would be -4 for the radius. And the x would be our cosine theta. So that is -4 times the cosine of 3 pi over 2, but that is 0, so that's 0. And y is our sine theta. So that's -4 times the sine of 3 pi over 4, but that is -1, so this becomes 4, and we're back to 4, 0. So it looks like we have 2 points of horizontal tangency. We have a horizontal tangent at 0, 0 and at 4, 0. Okay, so here's our answer here. Let's look at the graph to confirm that that's true. But we've already plotted this, and sure enough, at the point 0, 0, the tangent line to that curve would be horizontal, and at the point 4, 0, the tangent line is horizontal. Right, so a lot of work. And we're not done yet, because now we need to find the equation of a tangent line at a given other angle. Okay, so for this third part, I'm going to remind myself of the goal. The goal for a tangent line is to fill in y minus some y equals the slope times x minus some x. Okay, so to get the x and the y, what we'll do is just plug this angle into equations for x and y. So x is r cosine theta, right? But it's equal to r is 4 sine theta. So it's 4 sine theta cosine theta. And since I'm doing this at theta is pi over 3, this would be 4 times the sine of pi over 3 times the cosine of pi over 3. So on a unit circle, pi over 3 is here. And that means we have the x-coordinate is 1/2 and the y-coordinate is square root of 3 over 2. So this is going to be 4 times the sine, square root of 3 over 2, times the cosine, 1/2. 2 times 2 is 4, which will cancel that 4, and we get square root of 3 for the x. The y will be r sine theta, right? But the r is 4 sine theta times another sine theta. So this is 4 times sine of pi over 3 times another sine of pi over 3, which would be 4 times the square root of 3 over 2 times another square root of 3 over 2. So that's going to be square root of 3 times square root of 3, which is 3. So that means that the point on the curve is x is square root of 3, y is 3. So that means this is going to be y minus 3 equals some slope times x minus square root of 3. Now my last bit is to plug in the slope. Okay, so for the slope, we know the slope is dy dx. Always that, because we're graphing on an xy plane. But in polar, this is dy d theta divided by dx d theta. Right? So I'll have to take those two derivatives. Here's my equation for x over here. I already plugged in the r, right? And here's my equation for y, right? Which is also 4 sine squared theta. Okay, so dy d theta is the derivative of this equation, which is 8 times sine to the first times the derivative of the inside, which is cosine. And dx d theta is this equation, which requires product rule. So that's going to be first times derivative of the second plus second times derivative of the first. Okay, so let's see. I can maybe simplify that a little bit. This slope is going to be 8 sine cosine. Now on the bottom, I'm going to take a 4 out. And then that's going to be cosine squared minus sine squared of theta. All right, so now I want to evaluate this at the particular theta, pi over 3. So this is going to end up being 8 times the sine of pi over 3 times the cosine of pi over 3, and then divided by 4 times the cosine of pi over 3 squared minus the sine squared of pi over 3. All right, so what are all these values? Sine of pi over 3 is the square root of 2, square root of 3 over 2. Cosine is 1/2. And then down here I have 4 times the cosine value, which is 1/2 squared. So this is 1/2 squared minus the square root of 3 over 2 squared. Right, so whatever this value is, that gets plugged in here. And we don't really have to simplify that. We can just write this as m if you want, and then write an m here. That would be acceptable. Even on the AP test, you can define symbols like that. All right, rather than spend a bunch of time doing fraction arithmetic, let's move on to the next example. So that was the example for derivatives. And for an integral, we're going to talk about the arc length. We know that the arc length for parameterized functions is this. It's an integral from some starting to ending parameter value t, and we take in the integram the square root of dx dt squared plus dy dt squared. Okay, so the only thing that changes is now we have functions for x and y that end up as functions of theta. So we can use the same thing except switch to theta as the parameter. I'm not going to go through it here, but you're welcome to pause and look at the screen. If you carefully plug in the formulas for x and y, you can derive a third equation for arc length that's useful for polar. It's integrated over the parameter, which is the angle theta. And that means we start and end at an angle, and in the integrand, it's the square root of the r function squared plus the derivative of r with respect to theta function squared. Okay, so we will use that to solve two quick examples. These will be much faster than the other examples. All right, last two examples to finish this off. Find the arc length of the top half of the cardioid given by this. So we will use technology to graph that. Let's see. Let's clear this out, and we'll put in 2 minus 2 cosine theta. Okay, so if I graph this, zoom 6, it's a cardioid. Now let's zoom in quite a bit to see what's going on here, maybe out to 4. So negative 4 to 4, negative 4 to 4. Okay, there we go. And I'll square it up to look a little nicer. Zoom 5. Okay, this is what's happening here. I'm going to sketch that. Looks like we don't go all the way to the origin. Yeah, because if I put theta is 0, well, actually, if I put theta is 0 in here, that is 1. So sure enough, it does actually go to the origin, and it goes to 4. All right, so this looks like this. So we have something to reference. Okay, it is a cardioid that does something like that on both sides. Okay, so we want to find the arc length of the top half. Our goal is to find this length here specifically. Okay, so the first thing is we have to figure out where theta has to start and stop to trace that much out. What I would do for that is you can just experiment in the calculator, but you can also say what's unique about these 2 points are those are places where the y is 0. Right? So if I say, okay, y has to be 0, and y is r sine theta, and the r is given by 2 minus 2 cosine theta times sine theta, then that means that for this to be true, either the sine of theta is 0, or this 2 minus 2 cosine theta is equal to 0, which would be 2 cosine theta equaling 2, which would be cosine theta equaling 1. So where on a unit circle is the sine of theta 0? There and there. That could be at theta is 0 or pi. And the cosine is 1 at theta is 0. That suggests that maybe this is when theta is 0, and this is where theta is pi, which would actually map out to the graph, but you can't always assume that's true. So to verify that result, we'll go to our calculator, and we'll just restrict the domain here, the domain that we're graphing. Right now we're graphing from 0 to 2 pi, but what if we graph from 0 to 1 pi, and then just regraph that? Sure enough, that does only produce the top half. So I always use technology, if possible, to verify that I've got the range. We're going to be integrating from theta is 0 to pi. So then all we got to do is take this equation here and just fill in the values. So let me write it over here. The arc length, okay, let's use a darker color. Arc length is an integral from a starting angle to an ending angle of the square root of r squared plus the derivative dr d theta squared integrated over an angle's theta. All right, so r we already have, but we're going to have to figure out what dr d theta is. So dr d theta that's a constant, so its derivative is 0. The derivative of cosine is negative sine, so this is positive 2 sine theta. So this is going to be an integral square root of the r curve, 2 minus 2 cosine theta squared, plus the derivative curve, 2 sine theta squared d theta, and we're going to integrate from 0 to pi. Just so that we can see the number here, let's go ahead and do this with math to fractions. This math 9 here. So if we do math 9, I can go from 0 to pi, and then in the integrand we have the square root of parentheses 2 minus 2 cosine variable, close that, close the parentheses and square it. So that's the r squared, plus the derivative expression 2 sine theta, close the sine, close the parenthesis and square it, and then I'll go ahead and indicate the there. Okay, so this time we get 8. All right, so this is equal by approximation to 8. And does that make sense? If I look at the graph here on the scale, let's go back to the graph. This is 4, so yeah, this distance here would be 4. I could definitely believe that this is going far enough out here to travel a complete distance of 8 for that arc length. All right, so that's that example. One last example. Find the arc length of the curve, and in this case, they mean the entire curve. So let's graph it first to see what it looks like. I'll go here and replace this. This is going to be some kind of a rose. 3 theta. All right, and then if I graph that, let me just graph it as is. Yeah, that's good enough. We can zoom in a little bit, I suppose, but I think this is fine. Now, we do want to verify how far do we have to go around to, actually, let me sketch that so I can make this next comment here. If you have a rose that, let's see, looks like this. So it's got a petal like this, and a petal like this, and a petal like that. Okay. These are all starting and stopping when the radius is 0. So to try to figure out where we start and stop, I'll start with this little equation, r is 0. R is 2 sine of 3 theta. That has to be 0. Dividing by 2, that means sine of 3 theta must be 0, which means 3 theta has to be all the angles where the sine is 0, right? So that could be, let's say, for example, that could be 0, it could be pi, it could be 2 pi. We could even have negative pi if we want. Okay, so what I'm going to say is then if you divide everything by 3, you get theta is 0, pi over 3, 2 pi over 3, and then this would continue to 3 pi over 3, which would be pi. Okay, so since there are 3 petals here, I suspect that we're here when theta is 0, we're here again when theta is pi over 3, we're back here again at 2 pi over 3, and then we're back here again. So probably each one of these is one of the petals. Okay, which means we really only have to go from 0 to pi. Okay, to verify that, we're going to take our calculator and restrict this range. So let's say we went from 0 to pi over 3. That should give me 1 petal. And sure enough, it does. If I were to go from pi over 3 to 2 pi over 3, that would give me a different petal, right? And that means if I go from 0 all the way to pi, so if I go from 0 to pi, that should cover the entire 3-petal range. And that's it, exactly. So 2 pi would actually have gone around that twice. So this is where you got to be careful. It seems like to cover this whole thing, you'd go around 2 pi, but actually the theta is like a parameter, so it may only need to go pi to do that. All right, so I'm going to need the derivative. So let's find the derivative dr d theta. Okay, 2, the derivative of sine is cosine of 3 theta times the derivative of the inside, so it is 6 cosine of 3 theta. We can therefore make the integral, which is an integral we now know from 0 to pi of the square root of the r equation to sine of 3 theta squared plus the derivative equation squared, integrated over d theta. And if you put this in a calculator, you get that it's 13.365. All right, that is the last of the examples. I know these were kind of long, but I tried to pick ones that covered the sort of typical things that come up. So hopefully that gives you enough to be able to try some practice with homework.